Hello friends, I welcome you all to this session on power plant engineering. So in the last lecture we have seen that how to draw Rankine cycle. That means a cycle which is comprised of four major processes. What are those? Let me draw it here and then you will remember. I am drawing it in TS diagram. So the processes are, so here the first process is reversible adiabatic expansion, which happens in case of turbine, and in this case we get the shaft work. Then the second process is isobaric heat rejection, which happens in condenser where the heat loss takes place. Then comes reversible adiabatic compression, which happens in pump where the pump work we supply to increase the pressure of water. And then the the isobaric heat addition in boiler. Now, four processes we have in general. So let us do one by one, but let us take process 4 to 1, that is in boiler. So if you look this inside boiler, if we apply first law of thermodynamics for flow process, then we can say that the total amount of energy which enters in the boiler plus the heat transfer will be equal to the energy which is exiting plus the shaft work. This is your steady flow energy equation. So if you neglect the kinetic and potential energies and assume that 1 kilogram of water is flowing throughout the cycle per second, that is, if you say that per unit mass it is happening, then you can see that the energy which is entering here is at 0.4, that is enthalpy. So it is H4 plus the heat input, which is Q dot 1. Energy exiting at 1, so it is H1, and there is no work involved in process 4 to 1, so this is 0. So therefore heat input is nothing but the increase in enthalpy of the fluid from 4 to 1. So this is basically for the boiler. Now comes turbine. So if you look the turbine, inside the turbine, what happens? Inside the turbine, the steam pressure loses and we get shaft work. So again, if you apply the steady flow energy equation, so the energy which is entering at 0.1, so that is enthalpy at 0.1 plus, as this is adiabatic as well, reversible and adiabatic, so need no heat interaction, and that will be equal to energy exiting at 2, and the shaft work which we are getting is W dot shaft. So the amount of work which we will be getting from the turbine will be H1 minus H2. Okay, now comes the condenser, that is process 2 to 3. The turbine was process 1 to 2. So inside the condenser, the steam enters at 0.2, low pressure steam, then heat loss happens and we get saturated liquid. So energy entering, that is H2, as we are writing per unit mass everything, plus the heat transfer, but this is a heat loss, so it is minus Q2 dot is equal to the energy at point number 3 exiting, that is H3. No shaft work is involved, so the amount of heat loss, I have taken already the magnitude, so this is nothing but the heat loss magnitude, so this will be equal to H2 minus H3. So what is this? Don't get confused, this is nothing but the magnitude of heat loss. This is the magnitude of heat loss. Okay, now finally comes the pump, which is this process 3 to 4. Now inside pump, what is happening? We are supplying work so that the pressure can be increased, isn't it? So this is 3 to 4. So now energy is, and the fluid is entering at point 3 with energy H3 and exiting at point 4 with energy H4. So energy entering H3, no heat transfer because this is reversible adiabatic, and energy is exiting with H4, and then the shaft work and the work basically, and this time it is work done on the system, so it is minus. So WP, W dot P is nothing but H4 minus H3. Again, I'll tell you that this is what? This is just the magnitude of pump work. Pump work is done on the system, that's why we have taken this negative sign here. So magnitude of pump work. Okay. Now, also in reality, what we do is we normally won't be having this H4 so swiftly, but we only having the pressure. So what can be done? We can apply the work done in case of ideal work done in case of an open system. So if we do that, you all know that the first law when combined with the second law says that TDS is equal to DH minus VDP, isn't it? Okay, so now for reversible adiabatic, this term will be 0 and this DH will simply be equal to VDP. Very good. Now if you integrate it from 3 to 4, then what you will be getting? You will be getting H4 minus H3 is equal to integral 3 to 4 VDP. But how to solve this? Because we don't know the relation between V and P here. But in general, if you look this process, the liquid at state 3 is being compressed, means increased its pressure to 4. So what is happening? The liquid, you all know, it is more or less incompressible for ordinary pressure ranges. So the density of that fluid will not change much. So likewise the specific volume. So whatsoever the specific volume at point 3 is there, we can approximately say that it is same as at point 4 because of the liquid. So what we can say, V3, because we can calculate V3 very easily from the steam table, and then it is nothing but P4 minus P3. And what is H4 minus H3? You have already seen this H4 minus H3 is nothing but the magnitude of the work done, work transfer in the pump. Okay, so in this way you can solve for the pump work. Now if you are interested in finding out the efficiency, so efficiency of this Rankine cycle will be what? Net heat transfer to that of net work done, or or you can simply say net work done, let's say. So what is the net work done? It is work done in case of turbine, that is the shaft work, minus the pump work divided by heat input. So what is that? Shaft work, it is H1 minus H2. Look here, it is H1 minus H2, and the pump work magnitude is H3 minus H4, and this divided by the heat input, that is Q1, and Q1 dot is H1 minus H4. So friends, in this way you can evaluate the efficiency, or what you can do is you can also write in terms of heat interactions, that is Q2 dot by Q1 dot, and that will be equal to 1 minus, what is Q2 dot? Q2 dot, it is H2 minus H3, so H2 minus H3 divided by Q1 dot, which is H1 minus H4. So whichever is easy for you, you can do it. Okay, now that is how we evaluate the effectiveness, or what we say, the efficiency of a power plant. But apart from this, there is one more important thing that normally real practice in case of a plants, that is called as steam rate. So steam rate, what is steam rate? Steam rate is basically the capacity of steam. It is how defined. It is defined as the rate of steam flow required to produce, rate of steam flow required to generate unit shaft work. This is one of the parameter. Okay, the more the steam you will be requiring to generate unit amount of shaft work, the less efficient the turbine will be, है ना? And as well as there is another factor which is used in contrary to this efficiency, and that is what we call as heat rate. So heat rate. Now, how we define heat rate? Heat rate is defined as the amount of heat required to generate unit shaft work. So this is net work. Okay, and if you look this closely, this is nothing but the inverse of efficiency. I can write this in words that amount of heat input required to generate unit work output. Here, work output means net work output. So, if you look this closely, it is inverse of, if I write heat rate, then heat rate is basically nothing but inverse of efficiency. So, what this is Rankine cycle efficiency. So, what we say that for a steam power plant to work as a efficient unit, the efficiency of that Rankine cycle should be high. Higher the efficiency, the better the working. Whereas in terms of heat rate, what we say, if the heat rate of the power plant is low, then we will be saying that power plant is working efficiently because they are inverse. So in this way, we can comprehend the Rankine cycle. And in the next lecture, we'll be learning about the uh, because right now what we have done is, if you look, we have taken 4 to 1. We have not considered economizer, evaporator, and superheater separately. But we should also understand that what is the fraction of energy taken up by one and so on. So in the next lecture, we'll be learning about that. So in this lecture, till this point only, thank you very much for watching it.